Hello everyone, and welcome to this module on content addressing in IPFS. Content addressing is a very important and foundational principle in the IPFS system, and therefore it's going to be very useful to understand the rest of the subsystems of the IPFS architecture. In this module, we're going to start by some motivation on why content addressing brings benefits to the system. Then we're going to dive into more technical details of how content addressing is actually realized in IPFS. And finally, we are going to wrap everything together and look at the anatomy of the IPFS Content Identifier, or CID. So location addressing is what we use in the internet today, and it's mainly used in the domain by the domain name system, the DNS system, where when we ask for some content from the network, the DNS system is going to point us to a specific location, or in other words, an IP address, where the content that we have requested through the URL is stored. However, the URL only points to a single copy that is stored in a single location. If that copy disappears, we have no way to find out where alternative copies of the same content are. It is also not possible for a user to validate the integrity of the content. It is not possible to say if what we have requested for from the network is what we have actually received. Finally, there is no request aggregation, which results in inefficient use of resources. If two users that are placed in the same location, in the same geographic location, ask for the same content which is stored somewhere far away, then the network is going to transmit those bits twice from the remote server to the users requesting the content. We believe that this can be better handled. Instead of using location addressing and being bound by the DNS system to one location, one IP address where the content lives, instead we can use content addressing and basically ask any host if they have the content and then choose the closest copy. The address of the content is derived from the content itself in content-based addressing and not from the location. So it is because it's very common to have several copies of the same content in several different servers or user machines or locations around the internet, we do not want to be bound by one specific address, but we want to explore all opportunities and instead choose the closest copy to be delivered to our computer. In effect, what we want to do is go from a URL-based model, which is shown here as example.com, which translates through the DNS to a location, an IP address. We want to go to something that looks like this, which is a content-based address. And in this particular case, it's the content address of a PNG image of the cat. Therefore, we want to get the content of this image and have it as the direct representation of what we want to ask the network for. The content identifiers in the IPFS system are basically hashes. You can see two different versions of them down here, CID version 0 and CID version 1. And those hashes include some metadata. The metadata can very simplistically be the hash that has been used in order to produce the CID, the hash that has been applied to the content in order to get the CID. This is very important, and as we're going to see, gives us many opportunities. CIDs are also self-describing because you can look at them and at some and in specific cases you can understand out of it several different characteristics of the hash. So in this case, for example, we see that the hash, this hash starts with QM, which represents the CID version 0, and therefore we know how to process this hash from now on. In this case, the CID version 1 here starts with B, and we're going to see why this gives us more information about how to process this CID. In that sense, content identifiers in IPFS are self-describing. They include information that help us process them. By having CIDs represented as hashes, we can achieve a few different things. We can achieve deduplication because identical data can be verified by the content's address. In turn, this enables caching and saves resources and provides faster access to content. It provides self-certification as well. The content is authenticated by its address and not by a certificate authority. Therefore, the user can be sure that what they requested for is what they have actually received on their computer. It provides immutability. If the content changes, if a single bit in a content changes, the resulting hash is going to be totally different. This is a characteristic of any hash function and is used in producing the IPFS content identifiers. With this, we can have integrity checking, which we're going to see with an example here. So let's assume we have this piece of data, this document. We apply a hash function to it, and we have the resulting hash or fingerprint. Now, if we want to publish that piece of data, what we do is that we can send the fingerprint or the hash, the resulting hash of the content to others that we want to access the content. What these guys are going to do is that they're going to request from the network this fingerprint, this CID. They're going to receive this data, and what they can then do is apply the same hash function to the data that they have received, and then compare the resulting hash of what they received to the one that we have sent them and what they have, the one that they have requested from the network. If these do match, then this means that what they have asked for is what the network has sent them. If they do not match, then this means that either someone has tried to mess with the data, someone has tried to change the data before sending it to their computer, or that there has been a transmission error on the wire on the way to our computer. In this case, the user can just discard the data and request the content again. This is a very important property that gives lots of power to the user and takes it away from having to put trust in external systems in the network. Overall, the IPFS components can be broken down into those 4 parts. We have content addressing, which is what we're going to be discussing today. We have content discovery and routing, content exchange, and then some extensions to the content addressing part in order to enable IPFS to deal with dynamic mutable data. These 3 parts are subject to different modules that are going to follow on after this. So let's dive into the technical part and see how IPFS actually realizes content addressing. First of all, we have chunking. Chunking has been traditionally used in communication networks because it's simply better to deal with smaller pieces of data rather than big chunks, big objects in the size of the file. Now, this provides some extra benefits, which are summarized here, and we're going to go into each one of them in turn. First of all, we have deduplication. What this means is that as we break down a file into chunks or a folder into chunks, we realize that we might have the same identical data reappearing twice or more times within the file or the folder. What we can then do is, of course, not store all the pieces individually, but store only one copy of these green blocks here, and therefore optimize the system's storage requirements. What we can also have is what is called piecewise transfer. So if one part of the data that we have requested arrives in error because of some transmission error on the wire, then we can just discard this part and request again this part only, instead of having to discard all the previous parts that we have received and having to receive again, having to make the network transmit again the entirety of the file to our computer. Finally, we have what is called random access. We can think of that as a YouTube video where we just want to watch the second half of it and not the first half, and therefore we can jump straight into it. And instead of having to download everything to stream everything and make the network transmit everything to our machine, we can jump straight to where we want to watch the YouTube video from and carry on from there. This, of course, brings tremendous bandwidth optimizations to how the network overall operates. Okay, so now we have data, but how do we link data together in order to make the most efficient use of the chunks we have? In IPFS, chunks are connected in what is called Merkle-directed acyclic graphs, or Merkle DAGs. In Merkle DAGs, similarly to Merkle trees or hash trees, we have every chunk that is represented as a node. The hash of the chunk is the address of the node, and the address of every node is embedded in the parent link. What this means is that if we have the address of a node, then we can compose off of that the addresses of all these nodes' children. This is very important, as we're going to see later. What is not possible with Merkle trees, though, is for a node to have multiple parents. Effectively, what we want to achieve with Merkle DAGs is that every node in the DAG graph being accessed independently and have it become its own entity. This is very important because it enables deduplication. That is a very important principle, as we have already seen. So let's see this with an example as well. We have the previous file, and what we want, we have the chunks or leaf nodes of the graph, and we group two of them in order to produce the parent node, and the same for these two. Then, out of going one step further up in the hierarchy, we have these two nodes, which we combine in order to produce the parent node, which is, in this case, it's the root node. The chunking sizes here all depend in something that in the IPFS ecosystem is called UnixFS, and can be different. But for our example here, what we see is that the two green chunks that are identical, they point to different parents, and therefore we are not able to achieve the deduplication that we talked about before. We have to store this chunk twice in order for it to be accessed from the parent nodes. But we can do better. Deduplication does not only exist at the object level, as we've seen in the beginning, but exists also at the chunk level. So what we want to be able to do is have this chunk appearing only twice, this node appearing only twice, and being linked both from this part of the parent node and from this part of another parent node. In this case, we see that we do not have to store the green node, the green block, twice. We can only store it once and point to it from two different parents. This is a very important property. I encourage you to go to dag.ipfs.io and look and upload there a file which is then broken into, there is a nice visualization that breaks it into a DAG structure, and you can play with different chunking sizes and see an IPLD node visualized. Now, we talked about chunks, we linked chunks together. Now we want to go from data to data structures. With in IPFS, this is done with IPLD, the interplanetary linked data. which provides the standards and formats to build data structures based on Merkle DAGs. So you can think of an IPLD graph as a tree of folders similar to the one that you have on your computer, which there is a root node and then there are subfolders and files in them. Now, what we can achieve with IPLD and all the different standards and formats is to link from different parts of the same directed acyclic graph, or from even different ones, we can link to specific nodes. This is independent of what the nodes or the data itself has been encoded with, has been hashed with, because all these are the metadata that we talked about in the beginning that gives us the option to include in the CID and therefore translate the data the way we want. So as an example, as a representation, we can think of a piece of text, a paragraph of text that can be represented both in a TXT file, in a text editor, but it can also be put in a Word document. The content itself is the same, and if anything in that changes, the hash of the content is going to change. But as long as they stay the same, the content is the same, whether it is in a TXT editor or in a Word file. Now, you can think of that as the IPLD being able to identify that this paragraph of text is within one program or another, and therefore apply the correct formatting algorithms to it in order to extract the final content, which is what we're interested in. In that sense, with IPLD, we're not only going from location-based addressing and a location-based identifier, such as this URL, to a content-based identifier, such as this hash, but what we can also do is we can ask anyone with the content to serve this, independent of their location, but also independent of the encoding that they have, or hash functions, or whatever other serialization protocol they have applied to the content itself. This is a very powerful property because it allows us to link to IPLD nodes that might be stored in different locations, in different IPLD structures, in different file systems. Now, let's go to the final part on the anatomy of the IPFS CID and summarize all of the things that we have seen and see how the IPFS CID uses it. So we have seen these, that the CID looks something like this. Let's go and see more in detail what this part can be broken down into. And the parts are shown down here. You have a multi-hash, a multi-codec, a CID version, and a multi-base. The multi-hash is a self-describing hash digest, which includes the hash that has been used to, that has been applied to the content, together with some other data that we're going to see. The multi-codec is a preset number that uniquely identifies a format, a serialization protocol, or some other transmission protocol. And the multi-base is the base encoding. Starting from the multi-codecs, the full list of existing multi-codecs to date can be found in this link. And there is a table there that looks like this. You have the name of the protocol or format that you want to use or you want to insert into this table. And this can be a protocol like IPv4, IPv6, or DCCP. It can be a serialization protocol such as CBOR or protobuf. And down here, we can see the code that is actually used in the IPFS CID. Now, the multi-hash, which is the part that we have seen in the slide above, it's a self-describing hash digest. What it has got is the hash itself, but it also includes the hash function, which is itself a multi-codec and is included there so that someone that receives the CID knows which function has been used to hash the content itself. And it also includes the length of the hash digest. Finally, there is the multi-base, which is a self-describing base encoding. And if there are different letters, so B is for base 32, Z for base 58, and so on. So if we want to break it down even more, we come to look at something like this. We have the version 1 CID that we used before, which starts with a B, and as we have just learned, this stands for a base 32 encoding. Now, this is used in order to know how to interpret the CID itself. From that point on, once we apply the base 32 algorithm, we go to a binary format that will look something like this. In there, we have the CID version. We also have a series then of multi-codecs, with the first one being used to know how to interpret the data. In this case is the DAG protobuf, and it has got this code. And after that, we have the multi-hash. We have the hash function, in this case, SHA-256. Then we have the length of the multi-hash, sorry, the length of the hash digest. And finally, we have the actual content hash digest. Now, these middle parts is the IPLD encoding. And when referring to multi-codec, it has nothing to do with any video encoding or anything. It's the IPLD codec or multi-codec. So we see that these format down here, if applied to this binary format, we see that the multi-hash goes to this part here and to the right. Then we have the multi-codec, which helps us interpret the data. Then we have the CID version. And finally, the base is the first part, the first letter in the CID. And this helps us a lot in order to go to the binary format, as we mentioned. Now, the same CID, the same hash, the same actual hash can be represented by a CID version 0. I strongly recommend going to cid.ipfs.io and inserting those two CIDs there, which will give you something like this. It's going to be the CID that you're going to put in this field here is going to be broken down into all its different parts. And interestingly, you're going to see that the hash digest, this string down here, is going to be the same for both of these hashes, for both these CIDs. This is very interesting and very important because it tells us that with this set of values here that are the metadata that we mentioned in the beginning, we can represent the same piece of content in several different ways, using different hash functions, using different multi-codecs, different serialization formats, or different encoding algorithms. Now, a CID is commonly thought to be the hash of the file in bytes. This is actually wrong. And what we have to understand is that the CID, in particular, the multi-hash part, the hash, applies to the DAG representation of the file and not the file itself. So when the IPFS system is producing a CID out of the file that has been added to the system, it will first construct the IPLD DAG graph, and then it's going to apply the hashing that we have seen before to every individual leaf node in that tree. This concludes this module. Thank you very much for watching. We hope you enjoyed the new knowledge that you got out of this module, and please feel free to reach out with questions or get involved in the community. Thank you very much.